Hello and welcome back to Homework Help for Math 2. Today we're going to be looking at Unit 8, Circles, Angles, and Shapes, Lesson 3, Pied. Starting with the Ready section. The U.S. Department of Justice's 2010 American with Disabilities Act, or ADA, standards of accessible design require that the number of van-accessible parking spaces compared to the number of designated accessible parking spaces be 1 out of every 6. Okay. So again, we're comparing van-accessible parking spaces to just overall designated accessible parking spaces. Okay, so we have a ratio here. Question number 1. If a mall has 42 parking spaces designated as accessible, so that's the total, how many spaces must be identified as van accessible? Okay, so we are told that our ratio of van accessible to total, according to the ADA, has to be for every 6 spaces, 1 of them must be van accessible. That's our ratio. Now, in order to solve this problem, we can set up a proportion and say, all right, well, we don't only have 6 parking spaces, we actually have a total of 42 parking spaces. Right? And I want to solve for how many van accessible parking spaces does that require me to have. Now, there's a couple of different ways of solving this proportion. One way that you can always solve a proportion is by using cross multiplication. So if we're going to solve this using cross multiplication, it means that we're basically going to get rid of our fractions and we're going to take the numerator of one of our ratios and multiply it by the denominator of the other ratio. So for example, that means we could do 6 times x, giving us 6x. And then that's going to equal the product of my other numerator times my other denominator, which is 1 times 42, which is simply 42. And then in order to get x by itself, we divide everything by 6. And so we get that x has to be 42 divided by 6, which is 7. And we're talking about van accessible, so we're just 7 spots. In addition to using cross multiplication, if we go back to our original proportion for a second, what's nice about this proportion is that the numbers are pretty clean and they work out pretty nicely. Notice that if we go back to the proportion and look at the denominator, you can also say, all right, well, 6 times what gives me 42? Well, 6 times 7 gives me 42. So therefore, if I want x, we can just do the same thing in the numerator and do 1 times 7, and 1 times 7 is, of course, also 7. So with number 1, you can solve this either using cross multiplication, or we can just take our starting ratio and increase both the numerator and denominator by 7, or a factor of 7, and then that will give us 7 over 42, which means we need 7 spots. Question number 3. Most Costco parking lots average 3 designated van accessible spaces. Based on the 1:6 ADA ratio, how many parking spaces in the lot are designated as simply accessible? So this is very similar to number 1. We are starting with our ratio of 1:6, and again that ratio is van accessible to just generally accessible. And again, we can solve this by setting up a proportion, which is just letting 2 ratios equal each other. So this time, we're told that our parking lot at Costco typically has 3 designated van accessible spaces. So this time we're actually given our numerator of 3. And then the question is, well, if we have 3 designated van accessible spaces, then how many total do we have? So this time we have x. And again, just like we saw in number 1, you can always solve a proportion using cross multiplication. So if I solve this using cross multiplication, we get 1 times x, which is simply x. And then that's going to equal my other product, which is going to be 6 times 3. Actually, I'll write it all out. So 1 times x equals 6 times 3. 1x is clearly x, and 6 times 3 is 18. So we end up getting 18 spots, and that is our answer. We can also forego cross multiplication and just look back at our original proportion and say, all right, what do we need to multiply 1 by to get 3? Well, clearly we're going to multiply by 3. So if you do the same thing in the denominator and you say, all right, well, 6 times 3, that gives us 18, which again is another way to get the same answer. And again, because these numbers work out pretty nicely, you don't necessarily need to use cross multiplication. But if the numbers weren't as nice, you might have to use cross multiplication if the numbers don't go evenly into each other. The next set of questions say, the directions say, we can make ratios between many different quantities. Trigonometric ratios of sine, cosine, and tangent are ratios between side lengths in a right triangle. Write the indicated ratios for the right triangles shown. First assigned question was number 6. So for number 6, we have triangle ABC. And if we don't have to do this, but if we wanted to label, so 60 is side A, 80 is side B, 100 is side C. And we have to fill in this table where we have to evaluate 6 trig ratios. And the first one is sine of A. Whenever I'm working on these kinds of problems, the way that I like to go about this is I will actually circle the angle that we're talking about, which is angle A. Then I'll say, all right, I'm going to actually start with the hypotenuse. All right, so in this triangle, I mean, there's no box at C, but clearly we're told that this is a right triangle, so clearly C has to be the right angle. The side across from your right angle is always the hypotenuse. So that means that 100, the 100 is our H. That's our hypotenuse. Now, because we're talking about angle A, the side that is opposite A is down here. So I'm going to label that as O. And then the leg that is adjacent to A is going to be 80. So I will label that as A for adjacent. Okay. So, and actually, I think the A, B, C is just going to further complicate this. So I'm going to get rid of them. We don't need them for this question. So now it really just comes down to, do I know the definitions for sine, cosine, and tangent, and can I reduce my fractions? So the definition for sine, as a reminder, sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. And tangent is opposite over adjacent. So now all I really need to do is just plug in O, A, and H for each of these, and then simplify, and I should be good to go. So for sine of A, my opposite is 60, and my hypotenuse is 100. So that is our quantity, and it is our answer. So now all we need to do is simplify this. So we need to simplify 60 over 100. If you don't have access to a calculator, you're going to need to identify, all right, well, what is the GCF of both the numerator and the denominator? And I want to divide that out from both. Well, it turns out that 20 is the largest factor that goes into both 60 and 100. So 60 divided by 20 is 3, and 100 divided by 20 is 5, and that is our final answer. Now, if you do have access to a graphing calculator, if you type in 60 divided by 100, and then press math, enter, enter, you'll get your 3/5. All right. So if you have access to a graphing calculator, it can reduce the fractions for you. If you don't have access to a calculator, you need to again find what is the GCF in both your numerator and denominator, and then divide that out. In both cases, you get a final answer of 3/5. Now for cosine, the definition for cosine is adjacent over hypotenuse. We already identified 80 as being our adjacent value for angle A. The hypotenuse is still 100. That doesn't change. And once again, my GCF between 80 and 100 is also 20. So if we divide out a 20 from 80, we get 4. And if we divide out a 20 from 100, we get 5. For tangent, my definition for tangent is opposite over adjacent. My opposite we've labeled as 60. My adjacent we've labeled as 80. And yet again, our GCF is 20. So when we divide that out, 60 divided by 20 is 3, and 80 divided by 20 is 4. And that's the left-hand side. Now, for the right-hand side of this table, notice that now we're talking about angle B. So what that means is I'm actually going to erase the markings on my sketch. Now we're talking about angle B, so I'm going to circle angle B. Well, I didn't really have to erase the hypotenuse because that doesn't change. 100 is always the hypotenuse. But now that we're talking about angle B, my opposite and adjacent are going to flip. The side that is opposite B is 80, and I should be saying leg here. The leg that is adjacent to B is 60. So I've relabeled my triangle now because we're talking about angle B. My definitions don't change. Sine is still opposite over hypotenuse, and the side that's opposite B is 80. My hypotenuse, as always, is 100. And my GCF is 20, which means this becomes 4/5. Notice the relationship with my values on the left. So we've already seen 4/5. For cosine, the definition for cosine is adjacent over hypotenuse. The leg that is adjacent to B is 60. My hypotenuse, as always, is 100. And my GCF is 20, so this becomes 3/5. And again, notice a pattern here that seems to be developing between sine and cosine of angles A and B. Tangent, definition is always opposite over adjacent in a right triangle. My opposite currently is 80. My adjacent is 60. And when I reduce this, I get 4/3, which also has a relationship on the left. So we're now done question number 6, and I would encourage you that if you have not spent any time looking at the patterns that have emerged in this table, I would strongly encourage you to try to internalize any kind of patterns that you're noticing between the left-hand column and the right-hand column. Very important for understanding right triangle trig. Next assigned question was number 8, and same directions. So now we just need to sort of identify our sides and plug in. So we're going to start by talking about angle A. So I'm going to circle A. 14 is my hypotenuse, because again, we're told it's a right triangle, and clearly angle C has to be a right angle, and 14 is across from the right angle, so 14 is my hypotenuse. If we're talking about angle A, then that means that 7√2 is my opposite, and also 7√2 is my adjacent. My definition for sine in a right triangle is opposite over hypotenuse. So we've labeled our opposite as 7√2. and our hypotenuse as 14. Now, in order to reduce this, we're going to sort of temporarily ignore the root 2. Okay, so the root 2 is there, and we have to account for it, but we're going to temporarily ignore it, and we're going to look at just 7 over 14. To reduce 7 over 14, we'll notice that the GCF is 7, because 7 goes into 7, and 7 goes into 14. So what that means is 7 over 14 reduces to 1 over 2. Okay? Now that 1 is essentially a placeholder, and because we also have the root 2 in the denominator, we don't really need the 1, right? You could say 1 root 2, but you really don't need the 1, so it's better to just ignore it and just have the root 2, because we don't need a placeholder if we have something else there. And then it's over 2, because the 7 over 14 reduced to 1 over 2. So our final answer for sine of A is root 2 over 2. The definition for cosine is adjacent over hypotenuse. We've labeled adjacent as 7 root 2. And our hypotenuse as 14. This quantity is identical to the one above it, so by the very same reasoning, this simplifies to root 2 over 2. And the definition for tangent is opposite over adjacent. And so opposite in this case is 7 root 2. Adjacent is also 7 root 2. Now, we know that anything over itself is 1, other than 0. 0 divided by 0 is undefined. But any non-zero value over itself is 1. And 7 root 2 is a value. It's an irrational number, but it is a value, and it's a non-zero value. So this simplifies simply to 1. Now, when we're talking about angle B, we can go ahead and do our little circle thing and hypotenuse and opposite and adjacent. But you're probably already realizing that not much is going to change here because opposite and adjacent in this case are identical. So the definition for sine is opposite over hypotenuse, and based on my quote-unquote new labeling, our opposite is 7 root 2, and our hypotenuse, as always, is 14. Well, this is exactly what we got on the left. So this again simplifies to root 2 over 2. Cosine is adjacent over hypotenuse, and so this is 7 root 2 over 14, which we've now seen multiple times. This reduces to root 2 over 2. And tangent is opposite over adjacent, which based on my current labeling becomes 7 root 2 over 7 root 2. And again, any non-zero value over itself is 1, and so this becomes 1. Notice that with question 8, we are dealing with a right triangle where both legs are congruent. That makes this an isosceles right triangle. And notice the patterns that have emerged when we are talking about an isosceles right triangle, which is a 45, 45, 90 triangle. And we'll move on to the set questions. The directions here say, use the given information to determine each length or area. And we'll start with question 9. 9 says that the area of circle M is 25 pi square centimeters. Find the area of one sector. Okay. So with this picture, I guess even though we're not explicitly told this, I think it is safe for us to assume that all of these sectors are congruent. So there's a lot of symmetry in this picture. And because they're congruent, it means that all of the central angles at M are also congruent to each other. Okay? So this angle, 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 and this angle. They're all the same angle. And because there's 8 of them, what it means is if I want the area of one sector, the area of that one sector is going to be 1/8 of the entire circle. because each one is an eighth, and you add them up, and there's 8 of them, and that's going to add up to the entire circle. And because we are told the area of the whole circle, all we need to do for number 9 is we just need to say the area of one sector is going to be 1/8 of the entire circle. And we are told that the area of the entire circle is, sorry, go ahead and fix that, is 25 pi. And we don't need the cm squared until the very end, so we'll just ignore the units for a second here. This is our answer. So now it just comes down to sort of how do we express this? Well, 1/8 of 25, when you have a fraction and you're multiplying by an integer like this, the integer just gets multiplied to the numerator. So this is going to be 1 times 25, which is simply 25/8 pi. And now we can have our units of cm squared. If you were to express this as a decimal, 25 over 8 is 3.125 pi cm squared. So notice that both of my exact answers involve pi. And if you were asked to provide an approximation, so that means we're plugging in for pi, you would get approximately 9.82 square centimeters. So the directions were a little unclear as to how they wanted our answer to be written. So if you want an exact answer using a fraction, that's our first answer. If you want an exact answer using a decimal, that's our second answer. And if you wanted an approximation, that is our third answer. Also, for number 9, notice that if we didn't recognize the whole 1/8 thing, we could also think of each of these angles as, well, 1/8 of 360, which is 45, and then our fraction simply becomes 45 over 360. Okay? But this is a whole lot of just kind of busy work because this is itself 1/8, right? So I don't think that doing any of that is really necessary for this problem. I think it's sufficient just to say it's 1/8 of the entire area, and then we just sort of go from there. Question 10. We're told that the circumference of circle B is 18 pi feet, and we're being asked to find the area of one sector. So notice that in this question, we're given information about the circumference, and we want to find the area of something. And whenever you have a situation like this, it's almost always going to be a good idea to get the radius first. Okay, the radius is a very important dimension of a circle, and so because we're not explicitly told the radius, and because we're translating between circumference and area, it's going to make our job easier if we get the radius first and then use that to find the area. So notice that we're told that the circumference is 18 pi feet. Well, the formula for circumference, well, the formula for circumference that involves the radius is 2 pi r. That is the circumference for any circle. And for this circle, we are told that this value comes to 18 pi. So we have an equation, 2 pi r equals 18 pi. Well, we have a pi on both sides, and we're trying to get r by itself. So if I take my entire equation and I divide by 2 pi, all of the pi's are going to go away, and the 2 on the left is going to go away, and I'm going to be left with r equals, and on the right we have 18 divided by 2, which is 9. And we could put units here if we want to. It's feet. So my radius is 9 feet. The question is, what is the area of one sector? And similar to question number 9, we're not really told that all of these sectors are congruent, but I think it's safe to assume that they are. that means that all of our central angles are also congruent. And so if we want the area of one sector, we have 6 sectors, and they're all congruent to each other, and all 6 of them combined form the entire circle. So the area of one sector is simply going to be 1/6 of the area of the entire circle. The area of a circle is pi times r squared, and we just solved for r. So this is going to be pi times 9 squared, and that is essentially our answer. Now we just need to clean it up a little bit. So 9 squared is 81, and 81 divided by 6 simplifies to 27 over 2 pi. So I did 1/6 times 9 squared, and that simplifies to 27 over 2, because you get 81 over 6, and the GCF of 81 and 6 is 3. So we divide out a 3 from both of them, we get 27 halves. So 27 halves pi, we're talking about feet, and it's area, and so it's square feet. So that is one version of our answer. If we want our exact answer to not have a fraction in it, well, 27 over 2 is 13.5. We still need the pi because we haven't plugged that in, and we're still talking about feet squared. So both of those answers are exact, and if we want an approximate answer, so now we're plugging in for pi, we get 42.41 square feet. So depending on what format you want your answer to be in, we have 2 versions that are exact answers. One involves a fraction, one involves a decimal, and then we have an approximate answer, and they are all in feet squared. Question 11. The area of the small sector of the circle is 20 pi square feet. What is the radius of the circle? Show how you set up your problem. So when they say the small sector, it means they're talking about that piece right there, right? So what is the area of that piece? Or rather, sorry, they're giving us the area of that piece. They're told that the area of the small sector is in fact 20 pi, and we're looking for the radius. So in order to answer this question, we want to think about how in general can we determine the area of the sector of a circle. So the area of a sector is, we're going to start with a ratio, and that ratio is the measure of the central angle of our sector, which in this case we can tell from our picture is 72. And then our denominator is the total angle measurement at the center. And now it's a circle, so it's going to be 360 degrees. We don't need our degree symbols here because it's a ratio, so they're going to cancel. So we don't actually need to put the degree symbol in this situation. So what we want is essentially this much of the entire circle. And so we want this much of our formula for the area of the entire circle is pi times r squared. Now r is what we're looking for. What is the radius of the circle? So we don't know the radius. So I'm just going to go ahead and put r. And we are told that this sector has an area of 20 pi. Okay. So right off the bat, we have pi's on both sides, and so we can get rid of those. So the pi's go away because we're dividing by pi on both sides, and so the pi's go away. So notice that on the left-hand side, we have 72 over 360. Well, if I want to get rid of 72 over 360, I can simply multiply by the reciprocal. The reciprocal of 72 over 360 is 360 over 72. And if I take my equation here and I multiply everything by that reciprocal, what's going to happen on the left is that my fraction is going to go away, and I'm going to be left with just r squared. Okay. Now, whatever I do to the left, I have to also do to the right. So what that means is I have the 20 that was originally there from my original equation. And again, in order to clear out the left-hand side, I multiplied by the reciprocal of my fraction, which the reciprocal we just identified is going to be 360 over 72. So if you're pretty clever here, you might be able to do this in your head, but I'm not going to risk it. So when I type this in, we get 20 times 360 over 72. And we actually end up getting a nice round number of 100. And the reason for that is because it turns out that 360 divided by 72 is actually an integer. It's 5. And recognizing that might not have been super easy, but that is, in fact, true. So anyway, we get 20 times 360 divided by 72, which is 100. So that means r squared is 100. If I want to undo squaring, I want to take the square root. So we're going to take the square root of both sides. So we get r equals. Now, in this context, we do not need the plus minus because we're talking about a radius, and a negative radius doesn't really make sense. So this is one of those situations where we're dealing with a geometry problem, and negative length doesn't really make sense. So we're not going to put the plus minus here, and we're going to say that just r is just the positive square root of 100, which is 10. And we're talking about feet. So our final answer here for number 11 is 10 feet for the radius. Question 12. Question 12 says the length of arc AC measures 16 pi. So arc AC is that piece right there. And so we are told that that is 16 pi centimeters. That's the length of that arc. And what we want is we want the area of the entire circle. So what is the area of the entire circle if we happen to know an arc length? Show how you set up your problem. So in order to answer this, we want to think about, all right, well, how do we determine the length of an arc? So if we want the length of arc AC, well, the length of an arc, we're going to start with the ratio of the central angle at B. And we can tell from our picture that that's 120. That's our numerator of our ratio. The denominator is the total angle measurement at the center of a circle, and a circle has 360 degrees. Again, we don't need the degree symbol here because they would cancel. It's a ratio, so all we care about is how they relate to each other. So we want this ratio of the area of the entire circle. And, oh no, sorry, we're talking about arc length. Sorry. So we want the circumference of the entire circle because it's arc length, right? So we want this much of the entire circumference. And the formula for circumference is 2 pi r. And actually, I forgot to mention this. The reason why we're doing this is because if we want the area, getting the area when you know the radius is relatively easy. So really with 12, the trick with 12 is getting the radius, because once you get the radius, this is not that difficult of a problem. So we really just need to figure out what r is. So we've introduced r into our equation. We're also told that this length of arc AC is 16 pi. So everything on the left-hand side equals 16 pi. Just like with the last few problems, we have pi on both sides. So those can go away because we're just kind of dividing them out. And then on the left-hand side, if we clean this up a little bit, 120 over 360 is 1/3. And if you don't recognize that, you can always use your calculator. But 120 is the GCF of both 120 and 360, so we divide it out and we end up getting 1/3. And then when we multiply by the 2, everything over here sort of simplifies to 2/3 pi. Right? That's what that entire left-hand side simplifies to. We still have the r. Oh, no, sorry, we got rid of the pi. I apologize. We're going to get rid of the pi, but the r is still there. And then that equals 16. Okay. So if I want to get r by itself, we're simply going to multiply both sides by my reciprocal. The reciprocal of 2/3 is 3/2. And so therefore, r equals 16 times 3/2. I'll even write it out. 16 times 3/2. So half of 16 is 8, and 3 of them is 24 centimeters. And so now for our final answer, now this is relatively straightforward. We'll do it over here on the right. The area of the entire circle, not the sector, but the area of the circle, is simply pi r squared. We just found r to be 24. So it's pi times 24 squared. 24 squared is 576. The pi is still there, and we're talking about centimeters, and area is a two-dimensional unit of measurement, so it's square centimeters. That is our exact answer, and it actually I didn't actually calculate the approximate, so I'm going to go ahead and do that now. So 576 pi. So 576 pi, 576 pi is approximately 1809.56. 1809.56. 1809. Oops. Don't need a. Let me just. 1809.56 cm squared. And those are our two answers. The exact answer is 576 pi square centimeters, and the approximate answer for the area of the entire circle is 1,809.56 square centimeters. As always, we'll wrap up with the go section. The directions here say, find the measure of angle A in each triangle. And our first assigned question was number 18. So we're looking for the measure of angle A, which is right there. So this is x degrees. And we have we're told that this is a right triangle. It certainly looks like a right triangle, but the directions tell us it's a right triangle. Because it's a right triangle, we know that 100 is the hypotenuse, because it's across from the right angle. And because we're talking about angle A, this is definitely going to be a trigonometry problem. This is a right triangle trig problem. And because we're talking about angle A, I think it makes sense to label our legs, 80 and 60, in terms of which one is opposite, which one's adjacent. So the 60 is opposite angle A. And then the 80 is adjacent to angle A. And I know that I'm using two capital A's here, but as long as we sort of are methodical, I don't think it's going to be that much of a problem. I think we're able to differentiate between vertex A and A for adjacent. So if I want to solve for angle A, or in this case x, we've assigned it the variable x, I want to set up a trig ratio based on the information that we're given. Now, in this problem, we're actually given sort of like more information than we need, because theoretically, we actually could solve this if we were only given two sides. Because we're given three sides, both legs and the hypotenuse, we actually have some flexibility here, because what it means is we can actually use any of the three basic trig functions. We could use sine or cosine or tangent. If we were given only two sides, well, unless we want to solve for the third side, we would be sort of locked into using sine or cosine or tangent. But because we know all three sides, we can actually just choose one and then we'll just go with that. So for 18, I'm going to go ahead and use sine. It's the sort of the first one, if you will. So our equation then is that the sine of angle A equals, now the definition for sine is opposite over hypotenuse. And because we're talking about angle A, it means that 60 is opposite and 100 is my hypotenuse. Now, as a quick side note, I'll do this over here. If you were to use cosine, that is perfectly fine. With cosine, your ratio would be 80 over 100. And if you were to use tangent, that's also perfectly fine, and your ratio would be 60 over 80. Either one of these would be perfectly fine. And again, we have this flexibility because we know all three sides. But I'm going to go ahead and use sine. We could simplify it if we want to. So before we deal with the trig, 60 over 100, they both have a GCF of 20, and so when we divide out a 20, we get 3/5. Turns out that this is a 3-4-5 triangle. In case you can recognize your Pythagorean triples, then gold star for you. Now, what I want to do is I want to get A by itself. I guess I could be using X, but I'll just use A. So we want to get A by itself, and as of right now, A is not by itself because it's kind of inside the trig function of sine. And what I want to do is I want to get rid of that trig function. And the way that we can get rid of that trig function is if I take my entire equation and I use the inverse of sine. Well, what's the name of the inverse of sine? Well, it's not very imaginative. It's literally just sine inverse. Okay? So the inverse of sine is called sine inverse, or arc sine. You may occasionally see this referred to as arc sine. So what ends up happening here is on the left-hand side, you have the sine inverse of sine. Well, those are, by definition, inverse operations, which means they cancel, right? Just like if you divide when you're multiplying or if you add when you're subtracting, they also cancel. So on the left-hand side, all of my trig cancels, and I'm left with just A, which is great. That's what I want. But whatever I do to the left, I have to do to the right. So I'm also taking the sine inverse of 3/5. Okay? So the measure of angle A is the sine inverse of 3/5. And this actually is our exact answer here. So it's that in degrees, essentially. And I guess we could say, the measure of angle A, like that. So the measure of angle A. That's our exact answer. However, I think in this context, it definitely would be helpful to have an approximate answer because sine inverse of 3/5 just doesn't look good, even though it is in fact exact. So to go take a look at our calculator real quick. So first of all, because we're using trig here, we have to make sure that we're in the right mode. Notice at the top of my calculator it says radian. Well, we're not dealing with radians, we're dealing with degrees. So what that means is I have to go to mode, and I have to go down to where it says degree, which is right there, and press enter. Notice that now not only is degree highlighted, but if you take a look at the top of the calculator screen, it now says degree. That's exactly what I want. So that's great. So I'm going to press second mode to quit. And now I'm going to type in, sine inverse is in blue and it's above sine. So I'm going to type in second sine to bring up sine inverse. And I want sine inverse of 3/5. And essentially what this is saying is we're asking the calculator to identify the angle that would result in a sine ratio of 3/5. Right? What is the angle that results in 3/5 as my sine ratio? And my answer is 36.87 degrees. So here, this is approximately 36.87 degrees. So we have our exact and kind of ugly looking answer, and then we have our approximate but relatively straightforward answer. Both of them are in degrees. We'll wrap up here with question number 20. So for 20, again, our directions haven't changed. Our directions say find the measure of angle A, which is right there. And we're told that this is a right triangle, which means this kind of has to be our right angle, which means 14 has to be our hypotenuse. There is I don't want to say difficult, but there's sort of a longer way of solving this problem and then a quicker way of solving this problem. I'll start with the longer way because the longer way you can sort of always fall back on. It's kind of a safe way of doing this problem. But then I'll also show you a pretty quick way of doing this before we get into all or after we get into all the nitty-gritty of what's going on here. Again, just like number 18, we're given sort of this overabundance of information. We are told all three sides. And again, we're talking about angle A here, so I'm going to just go ahead and label this. So that means that this is opposite and this is adjacent. And because we're told all three sides, opposite, adjacent, and hypotenuse, it means that if we're going to do this sort of the longer way, we have some flexibility in terms of which trig function are we going to use, sine or cosine or tangent. I'm going to go ahead and use tangent this time, just to mix it up a little bit. So if I'm going to use tangent, the tangent of angle A, the definition for tangent is opposite over adjacent. So in this case, opposite is 7 root 2, and adjacent is also 7 root 2. All right. Well, this is pretty nice because any non-zero value over itself is 1, and 7 root 2 is irrational, but it's definitely not 0. So that means that 7 root 2 over 7 root 2 simplifies to the much simpler version of 1. And again, I want to get A by itself. And if I want to get A by itself, it means I can take my inverse trig function of both sides. What's going to happen on the left is that the tangent inverse and the tangent are going to cancel, and I'm left with just A. And then on the right, I still need my tangent inverse, but I'm taking the tangent inverse of the number 1. Okay. So this is basically saying what is the angle that results in a tangent value of 1? Well, if you're a little shaky on the unit circle, you could go to your calculator and you could say, all right, well, we're in degree mode, so that's great. And then you say, all right, tangent inverse of the number 1, and it gives us 45. And it turns out that is our final exact answer. We don't have to give an approximate answer because that's exact. And we're done number 20. That's it. That's all we have to do. If you got to the second to last step here and you realized that the tangent of 45 is 1 because you've memorized those values in the unit circle, then that's great. If you could solve this question without using the calculator, that's great. That's a good sign. I also said that we can solve this in a much quicker method, and the much quicker method is to go back to the very beginning. I'm going to just erase all my markings here. And notice that in this case, 2 of our sides are congruent. So what that means is this is an isosceles triangle. Okay, BC is congruent to AC. And because it's a right triangle, it means that, well, if this angle is 90, the sum of my angles is 180, and in an isosceles triangle, these two angles have to be congruent to each other. The only way that that can work is if both of them are 45 degrees, because you need the sum to be 180. The right angle is 90, so my other two angles have to sum to 90, and they're congruent, which means it's literally just half of 90, which is 45. So sort of like the ideal way of solving number 20 is actually to not do all of the trig that we did, and actually just to recognize that question number 20 is an isosceles right triangle. And in an isosceles right triangle, your base angles, which in this case are A and B, are always 45 degrees. So if you notice that, then that's great, and you saved yourself some time. But no matter how you did number 20, whether you used trig or whether you used just sort of our knowledge of geometry and isosceles triangles, you should have gotten that the measure of angle A is 45 degrees.